Hello, Analysis 1A, specifically period 6. We're going to do a little thing that we did live in the other classes, but we're a little behind for some reason. Recall in Pre-Calc C, when seemingly for no reason, out of nowhere and connected with nothing else we were studying, I passed out a packet called combination trig graphs. And among the many functions in this packet was one that was sine x over x. And, I just decided, hey, we're going to graph this function. Okay, how do you graph this function? Well, it's required us to be, quite good at graphing functions. And, okay, there are many things to observe. One thing to observe is that the domain of this function is everything except 0, because I can take the sine of anything, and so the only thing I really need to worry about is that denominator being 0. Another thing to notice about this function is whenever the numerator is 0, it will be 0. So when is sine 0? Well, at every k pi. So we're going to get roots at every k pi. So that's kind of nice to know. What other kinds of properties can we say about this? Well, n behavior. What happens as n goes to infinity? And since we're talking about limits, we might as well just start talking about them. So what is the limit as x goes to infinity of sine x over x? Well, for very, very large values of x, the numerator is always going to be between -1 and 1. It's bounded, but the denominator is just going to keep growing and growing. So this is 0. And the limit as x approaches negative infinity of sine x over x is also 0. For the same reason, the numerator will be a number between -1 and 1, but the denominator is going to grow to be a huge, in this case, negative number. And, what does this mean? This means that we have a horizontal asymptote. This horizontal asymptote is y equals 0. And this is actually a good example of a function with a horizontal asymptote in which the function definitely crosses this horizontal asymptote, because we have an infinite number of roots and they occur sort of infinitely often. I could have sort of saved a little bit of work here. I don't even need to really talk about what's happening as x goes to negative infinity, because I already know what's happening as x goes to infinity. And another thing to observe about this function is that it is even. Because both the numerator and the denominator are odd, so you pull the negatives cancel after you pull them out. And let's see, one more thing, maybe, this was sort of in the spirit of that packet. This was, I know this was months ago, but, let's get it back, which is that sine x is always between -1 and 1. And so, taking the positive case for a minute, so let's just assume that x is negative for simplicity. Then what do we get? We get that sine x over x is between -1 over x and 1 over x. So in other words, this function is bounded between these two other functions, the 1 over x and the -1 over x function. That's what we call the envelope of this function. And okay, since this function is even, then I can kind of wave my hand and say, the negative side of it is sort of doing the same thing. But if I wanted to continue the analysis for when x is negative, then when you divide through by x, you have to flip the sign, you get the kind of the other one. But all right, I think we've sort of proven our point, which is that this function is going to have a certain look to it. It's going to be bounded by these sort of hyperbolic asymptotes, we might call them now. And okay, how about the actual function? Well, we did things, right? We plugged in like pi over 2 and pi and 3 pi over 2 and boom, boom, boom. And we said, okay, what happens at pi over 2? Well, sine of pi over 2 is just 1 there, and so you're going to get 1 over pi over 2. In other words, you're going to land on the upper envelope. And then, of course, at pi, this function will be 0, because this function is 0 at every k pi. And yeah, If you plug in 3 pi over 2, sine of 3 pi over 2 is -1. And so, okay, a lot of effort went into this, which I'm skipping because this is kind of review or whatever. And something looks a little bit wrong, but I guess it's not. And this kind of doing this and kind of like doing this. Okay, so that was all basically easy and you know, not easy, but sort of a careful pre-calculus student who knows a lot about functions and their properties can reconstruct everything there is to say about this function. Now the big question was what happens as x goes to 0. And what happened in pre-calc C, in an idealized circumstance, if you happen to have been in a good mood that day and the class was engaged, you know, what happened was something very similar to the conversation that we just had in class on the second day of calculus, which is looking at the numerator and denominator and making kind of observations. And one observation is that when x is very, very close to 0, this denominator is very tiny, and so we should expect this function to be infinite. And in fact, most years, in most classes, people do speculate and conjecture that there is a vertical asymptote here at x equals 0 to this function, because the denominator, when very, very tiny, is going to cause this fraction to be huge. But then, what happened, potentially in this order, is that somebody else noticed that, well, when x is very close to 0, the numerator is also 0. And so we found ourselves back in pre-calc C, faced with this situation, which we now see is kind of central to calculus, which is that we have a tiny over tiny situation. And the numerator is very, when x is very close to 0, but what's left for us to do here is to complete this graph, is to analyze what's happening near 0. Of course, this function's undefined at 0, but I'm not interested in what's happening at 0. I'm interested in what is happening near 0. And the answer is that both the numerator and the denominator are very tiny near 0. Okay, so how did we solve this problem? We solved this problem by taking a close look at the sine function. And actually what we did back in pre-calc C was we went all the way back to the definition of the trig function, sine. And we recalled that sine is defined geometrically. So what is sine? It's the y-coordinate. And it's the y-coordinate of a point on the unit circle with a certain arc length. So the good way to do trigonometry is to think of the input to the sine function as being the length of an arc on the unit circle. And so the idea was something like this. You give me some real number, x, I wrap that real number starting at 1, 0 around a circle of radius 1, and wherever it terminates, I then define the sine function accordingly. And my definition of the sine function is that sine is the height. It's the height of this point when you take an arc length, when you take an arc of length x on the unit circle in this position. Okay, and it was after drawing this picture and recalling from, really this was pre-calc A, that you were first exposed to this definition. This is sort of the real definition of what sine is, using radians, that we conclude that sine x must be less than x, at least for small values of x. And therefore, I can look at this and I can see that this is definitely going to be like less than or equal to 1, this function always. And so the conjectures that perhaps this function had a vertical asymptote at x equals 0 were wrong. Okay, and then the final thing to do is to kind of finish it off and answer the question now, you know, what really does happen for tiny values of x? And to answer that question, what we need to do is we need to look at the behavior of these two geometric sort of pieces, this arc length and this half chord, when x is very small. So that's exactly what we did. we drew this. This is how we did it in pre-calc C, and this is how we're going to do it right now, which is to say, you can just draw this tiny little thing, let x be, very, very small. That's pretty small. And then, what is sine? Answer, it's just this height. So it's, and the idea here is that for very, very small values of x, there becomes almost no difference between this arc length and this height. And so already it seems, just by kind of eyeballing that these are basically the same. And if x becomes kind of like infinitely small, then were you to zoom in and zoom in and zoom in on the point 1 comma 0, you would find almost no difference between these two. Okay, and therefore, in our pre-calculus kind of vocabulary, what we concluded is that the end behavior, or not the end behavior, the local behavior of this function was that this was looking more and more like 1. And that's how we completed the graph of this function, and we felt pretty good about ourselves. Okay, so that happened, and then, we never talked about it again, or at least not many times again. Well, now we're in calculus, right? So all of this same conversation still applies, and now it's time to state it in the language of calculus, specifically in the language of limits. So if I were to summarize this whole thing that happened back in pre-calc C, I would say that the limit as x approaches 0 of sine x over x is 1. This is so important that I want to talk about it already on just the second day of class, and I would like to note that we're going to prove this fact more carefully, because what I did here was more of a kind of explanation or something like that, not really a proof, or at least this convinces many, but perhaps not everybody. So a more careful proof of this fact is coming, but for now let's just take it as a fact. Alright, why are we talking about this at this moment? It's because we have a worksheet, and the second problem on this worksheet was, this was number 2, the thing we were doing in class, the limit as x approaches 0 of 5 sine 2x over x. Okay, and how should we do this? Well, the very first thing we need to do is to recognize that there is something to do. That is to say, we should sort of first maybe kind of casually and naively just sort of ask ourselves, well, when x is really close to 0, like what's going on? The denominator is going to 0. What is the numerator doing? Well, okay, the sign, when x is approximately 0, 2 times a very, very tiny thing is very, very tiny. Sine of a very, very tiny thing is very tiny. 5 times of a tiny thing is very, very tiny. So this is a tiny over tiny situation. It's what I call a 0 over 0 situation. It's a limit in which both the numerator and denominator are infinitely small. And therefore, we cannot just use our emotions to determine what the answer is. We have to actually do some work. And what is the work that we can do here? Well, if we fully understand this limit, then perhaps we can build on that in some way. And in period 3 and 4, we got some suggestions, which is to apply a trig identity. So if we do that, okay, we get the limit as x approaches 0 of, instead of sine 2x, we write this as 2 sine x cosine x. And now I think we're ready to talk about what's going on, because what is sine x over x? Well, sine x over x is just going to 1. So we can sort of say that as x is going to 0, this sine x over x thing is going to 1. And what's cosine doing as x goes to 0? Well, as x goes to 0, cosine of 0 is basically 1, so this is more or less 1 too. And so you can already just eyeball the answer to this problem as 10, and that is the answer. And at this moment, that's kind of fine to just maybe say 10. But if you want to be a little bit more of a math teacher about it, you could maybe show some more work wherein you factored out a 10 and sort of expressed this. This must be, a rule or something, right? That that we can split up a limit into the product of the limits. That sounds like something that should be true, because after all, these are just numbers and they're sort of just being multiplied. So this limit we've seen is 1, or we're accepting it as 1 for the moment, and this is also 1, so the answer to this problem is 10. Okay, how long was that? That was 15 minutes. So, all right, period 6. We covered all of that in live in class on Thursday in period 3 and 4. So we gotta go a little faster to catch up with those guys. Welcome, rest of the class. I'm telling periods 3 and 4 to start watching now. And basically what we're going to do is just the rest of this Intro to Limits worksheet. Kind of meant as, group work in a certain way, but alright, no time for that Zoom school. So I typically then just go over it, the next class. So instead, we'll just do it all right now. So let's go. I'm kind of doing this in whatever order I feel like. So I'll do number 5 next. Just because it's kind of easy. It's the limit as x approaches 1 of x squared minus 1 over x minus 1. Well, if I try to see what's happening as x gets really close to 1, I observe that the denominator is very tiny and the numerator is very tiny also. So this is a 0 over 0 situation, and therefore I need to go do some work because I can't say what this is yet. That's an indeterminate form. All right, in this case, the analysis is, I think, pretty obvious, which is to just factor the numerator and then the x minus 1's cancel. And so we have that this is the limit as x approaches 1 of x plus 1, and that is just 2. So okay, that's kind of now 3 down, 5 to go or something. Okay, let's go. 6. 6 says, what is the limit as x approaches pi plus of cosecant x? Okay, this is barely a calculus problem at all. This is basically a pre-calculus problem. This is essentially asking like, hey, can you graph cosecant on demand? Well, I can, and it looks like this. It's 1 over sine, so it's going to be infinite whenever sine is 0. Sine is 0 at every k pi, and sine of pi over 2 is 1, so the cosecant of that will be 1, but sine of everything else between 0 and pi, it's the top of the unit circle. The sine will be a positive number that's less than 1, so the reciprocal of that cosecant will be a positive number which is bigger than 1. Okay, so that's called me just kind of talking it out, and for x values that are, or for angles that are in quadrants 3 or 4, we're in the bottom half of the semicircle, the bottom half of the unit circle, so that's sine is negative. So when you reciprocate, you get a negative number which is lower than negative 1. So anyway, that's the graph of cosecant. Hopefully you just know that by heart, or you can reproduce it in seconds. Alright, so what is this asking? This is just asking, what happens as x approaches pi plus? If x is a tiny bit more than pi plus, then the answer here is negative infinity. So okay, this was maybe the graphical approach. Potentially you could also have done the entire thing directly from the unit circle, and maybe that's even superior, because what is pi plus? Pi plus would be a point that's just a tiny bit more than pi, so sort of like there, for example. And what is cosecant? Kind of by definition, it's just like 1 over the y coordinate. So what is that point? Well, it's pretty much negative 1 comma a tiny bit less than 0 is actually a good way to label that point if we're thinking of it as being sort of just a tiny infinitely bit more than pi. So it's going to be a negative number that's a little bit smaller than negative 1, and the y coordinate will be a tiny negative, and so it was also possible to answer negative infinity that way, because it's cosecant is 1 over the y coordinate, so it's going to be 1 over 0 minus negative infinity. So whether you like to reconstruct the graph or whether you like to think about the unit circle, both are good. Okay, we push on. Number 3. This is one which people find pretty difficult, and it is really, I think there is a lot of benefit in sort of trying it and kind of getting it wrong and seeing what happens when you kind of make errors. But, okay, anyway, too bad. Here we are. We need to do this. Alright, what happens when x is very, very close to 2? Well, if x is very, very close to 2, then the first thing to observe is that this denominator is going to be pretty much tiny. So, okay, what about the numerator? Oh, well, 2 minus 1 is 1, the square root of 1 is 1, so this numerator is tiny also. Okay, so once again we find ourselves in a 0 over 0 situation. It's not really 0 over really 0 because I'm only looking at what happens when x is near 2, but it's a tiny over tiny situation. So we can't just use our imagination and feelings. We have to like really perform an analysis. And so some kind of algebraic analysis is going to be required here. Okay, and it's actually just very not obvious what the correct thing to do is right now. And it really comes down to the thing that's giving us kind of trouble is this square root of x minus 1. So just like, maybe just pause for a minute and just be like, you know, what is the square root of x minus 1? What does that even like mean? What is the sort of definition of that entire expression? Well, the square root of x minus 1 you can think of as, well, what is it? It's just like maybe asking, you know, what is the square root of 16, for example. How do you teach a 5th grader what the square root of 16 means? Well, it's the positive number which, when squared, is 16. And so the reason why the square root of 16 is 4 is because 4 squared is 16. So that's just what the square root symbol means. It is sort of saying the square root of 16 is the thing which, when squared, is 16. So what is the square root of x minus 1? It's the thing which, when squared, is x minus 1. Alright, what I'm getting at here is that built into the very definition of the square root of x minus 1 is its sort of potential to be x minus 1 if you were to square it somehow. And since that's like the definition, then I am not going to be able to like arrive at the truth of, or I'm not going to be able to use any property of this function until I can square it somehow. In other words, if the thing is, if the square root of x minus 1 is that which when squared is x minus 1, then in order to apply that definition in any kind of meaningful way, I need to do some squaring. So we ultimately have an algebra problem on our hands now, and this algebra problem is the problem of simplifying what's going on inside of here to reveal what's really happening. I need to figure out which is bigger, the numerator or denominator. Well, the only way I'm going to arrive at the truth is if I can get rid of this radical, so to speak, by squaring it. So what I kind of want to do now is just square that thing. But of course you can't just square random stuff just because you want to. Alright, what is the solution? The solution is an algebra trick, and I'm trying to introduce this trick to you in a way that makes it seem like not so much of a trick. I need to massage this expression in a way that involves, you know, squaring square root of x minus 1. Okay, without further ado, what is it that we're going to do? We're going to multiply by the conjugate. So if I multiply by 1 plus root x plus 1 over 1 plus root x plus 1, first of all, that is, of course, you know, allowed. Second of all, based on my experience with sort of algebra, I see this as kind of like a powerful technique. And the thing is that I do, whoa, that should say minus. Okay, so let's just sort of see what happens. What happens is that the whole idea of multiplying by the conjugate is that 1 minus root x minus 1 times 1 plus root x minus 1 is the difference of squares. And so that's going to give me 1 minus x minus 1. And down here on the bottom, I have sort of confusing stuff, I guess, to be honest. I have like this. Okay, so I seem to have created, you know, something that's even messier than the original, but I did square that x minus 1, ultimately. And therefore, I've sort of unpacked the kind of, the true meaning of this expression. Alright, why is this helpful? Because now, what do I get in the numerator? Well, I get 1 minus x plus another 1. So maybe I'll just write that. 1 minus x plus 1 over x minus 2 times 1 plus root x minus 1. What's up with that? Well, that's just 2 minus x up there. If that's just 2 minus x, then perhaps I even write it as negative x minus 2, since that's what it is. And now I see the whole strategy here to answer this problem was basically figuring out, sort of how big is that numerator for very, very tiny values of 2. And I didn't really answer the question how big that numerator was, but I really answered the question was sort of how big is the difference of the squares between those two things. And the answer is it's basically like x minus 2. Okay, so whether this feels like it flows to you or not, hopefully now, at least at the end of the problem, you see that we have succeeded, right? Because the numerator and the denominator can be canceled, and now I get the limit as x approaches 2 of negative 1 over 1 plus root x minus 1. And what's up with this? This is progress, because though this might not look much simpler than the original problem, this is now not indeterminate, because we can simply plug the numbers in. What is this doing when x is very, very close to 2? Well, answer, the top is just negative 1, and the bottom is 1 plus, if you plug in 2 here, you get 2 minus 1 is 1, the square root of 1 is 1. So in fact, the answer to this problem is negative 1/2. And I just would not have seen that coming. Really, you do have to actually do the algebra. Okay, what's left? Kind of want to be done with this worksheet. Let's do the rest of them really fast. Yeah, good. 7. Well, this is now maybe kind of similar. We're taking the limit as x approaches 4 of root x minus 2 over x minus 4. First thing to observe is that if you plug 4 in for x in the numerator, you get 2 minus 2, it's basically 0. And if you plug 4 into x in the denominator, you also get something which is basically 0. So this is again a 0 over 0 situation. And so again, I'm going to have to do some work to sort of get the answer. I can't just guess because the form that it is in is one which leaves me unable to make any conclusions. So let's see, what could we do? Well, building upon what we just did a few minutes ago, perhaps multiplying by the conjugate is a good idea. And so there are basically 2 ways to do this problem. This is a way, just multiplying the top and bottom by root x plus 2 over root x plus 2. And that is going to achieve what we kind of talked about a minute ago, which is sort of unlocking, so to speak, the true meaning of root x, which is the thing which when squared is x. So if I want to know what it is, I better square it. And the only way to square it is to write it like this. Okay, well, if we do this, what happens, we get the limit as x approaches 4 of, the numerator becomes, because it's the difference of squares pattern, x minus 4. And so this is x minus 4 over, well, down here on the bottom, don't distribute, just leave it as is, because it's perfect as is. And yeah, we can cancel this. And so this becomes the limit as x goes to 4 of 1 over root x plus 2. And squeezing it in here because I really want to, I've now done my work, and now it's no longer indeterminate. If I plug in 4, the square root of 4 is 2, so this is 1 over 2 plus 2. So the answer to this problem, which I did not see coming, is 1/4. There is actually a simpler way to do this problem, and this requires maybe some sophistication. If you're willing to see a couple steps in advance, then something you could do is actually just factor the denominator. This is not a kind of thing that we do very often, but once you see it, then you see it. X minus 4 you can think of as just root x minus 2 times root x plus 2. And this is sort of, kind of more efficient or something, or more elegant, more to the point. So then this cancels, and we end up in the same place, however. This is the limit as x goes to 4 of 1 over root x plus 2. So these are just kind of minor variant solutions. So that becomes a 2. This is 1 over 2 plus 2, so this is 1/4. Okay, 2 more to go. 8. 8 is something of it's either a trick or a typo, but here it is, x squared plus x minus 20 over x squared minus 6x minus 7. And this problem is kind of, begging you to factor it. And, well, you can factor this if you want. What happens if you factor it? You get the limit as x approaches 4 minus of, what's up there? It's x plus 5, x minus 4 over x minus 6, x plus 1. That's got to be right, yeah? And, no, 7. Jeez. X squared plus x minus 6, yeah. Okay, but now what happens when I plug in 4? Well, when I plug in 4 now, I just get a 0 up top, and I just don't get a 0 on the bottom. So when x is approximately 4, this is pretty much like 9 times pretty much 0 over, what's down here? Pretty much negative 3 times pretty much 5. So it turned out that all this factoring was kind of irrelevant. I could have just plugged in 4 directly at the beginning and gotten 16 plus 4 is 20 minus 20 is 0, but the denominator is just not 0. It's 16 minus 7 is 9 minus 24 is like negative 15 or whatever, which I also got this way. And so this is something that's pretty much 0 over a normal number, and so the answer to this is just 0. Okay, the final problem, yikes, is number 4. And number 4 is something of a, I don't want to call it a trick, I would call it maybe like a misdirect. So this is x minus 1 over root x plus 6 minus 3. And okay, if you tried this problem first by yourself, especially if it's only been a minute since you've done some previous problems, then one thing you might do, potentially, is just jump right in and try to multiply by the conjugate. But that's the kind of mindless algebra manipulation that I want to discourage. It's not a good idea to just mindlessly multiply by the conjugate. What is a good idea is to multiply by the conjugate with like a reason and a purpose. And do we have a reason to do algebra here? It turns out no. The first thing you should always try to do is just plug numbers in. What happens if I plug in 3? I get 3 plus 6 is 9, the square root of 9 is 3, 3 minus 3 is 0. But if I plug in 3 up here, I get 2. So this is not a 0 over 0 situation. This is a 2 over 0 situation. And I'm now ready to say that the answer to this limit is that it's just going to be something kind of infinite, or perhaps not existing. But a more careful analysis is going to require us to determine if the numerator is looking pretty much like a 2, like a regular positive number, and the denominator is very, very tiny. To answer this question is going to require me to figure out whether this denominator is a tiny positive number or a tiny negative number. And the answer is that it depends. It depends on whether the square root of x plus 6 is a little bit more than 3 or a little bit less than 3. And that depends on whether x plus 6 is a little bit more than 9 or a little bit less than 9. And that depends on whether x is a little bit more than 3 or a little bit less than 3. And so what we are sort of forced to do now is to consider first the limit as x approaches 3 plus, and then the limit as x approaches 3 minus. And some people are sort of very comfortable with this and maybe can kind of do this whole thing in their head. And other people maybe want to kind of write it all out and be a little bit more careful, at least at first. So I'll kind of be careful this time at least. What happens if I plug in a number a little bit more than 3? Well, a little bit more than 3 minus 1 is like a little bit more than 2. So that numerator is just going to be pretty much 2. But now, a little bit more than 3 plus 6 is a little bit more than 9. So we're taking the square root of a little bit more than 9 minus 3. Well, what is the square root of a little bit more than 9? Answer, it's a little bit more than 3. And now, if I subtract 3 from a number that's a little bit more than 3, that is going to be a tiny positive. And if I divide 2 by a tiny positive number, I get infinity. Whereas, if x is a little bit less than 3, that's what this symbol means, now this number up here is a tiny bit less than 2. Down here, if I add a number a little bit less than 3 to 6, then I get a number which is a little bit less than 9. And what is the square root of a little bit less than 9? It's a little bit less than 3. So that's 3 minus 3. Now if I subtract 3 from a number which is a little bit less than 3, that's going to give me a tiny negative. And the numerator is a little bit less than 2, but that sort of doesn't really matter. What matters is that the numerator is pretty much just 2. And if you divide pretty much just 2 by a tiny, tiny negative number, what you in fact get is negative infinity. So the full answer to this problem number 4 is in fact to pause, backtrack, compute these two separate limits, observe what their answers are, and to therefore conclude that I can really say almost nothing about this, right? I have to now say that this limit just does not exist. And the reason why it does not exist, I've just now shown in my work below, that the limit from the left is negative infinity, the limit from the right is positive infinity, and so this I can't say anything about this really. It's doing sort of two separate things on two sides of 3, and so we say it just doesn't exist at all. Okay, this is an introduction to limits. This is all, in some ways, just common sense. But if it's not common sense to you, then now you're seeing kind of how to think about this and how to reason it through it, and sort of how to write things down and show your work and stuff like that too, and the necessity for algebra. Okay, goodbye.